up here, we're on the back of the 4th page of the review, this Algebra 2 semester exam review. We're in this section here talking about exponential and logarithmic functions. I did a bunch of these on the last video, and I showed using Desmos, how you can just use Desmos to do the calculating for you. You just have to be able to do the rewriting right here from log to exponential and vice versa. You have to be able to go back and forth between those to be able to do what I'm showing you in Desmos, okay? So I'm down here on M now. So on M, we are given exponential form, but that x is up in the exponent, so we need to get it down by rewriting this in log form. When you are rewriting between the forms, your exponential or log expression has to be isolated. So that e to the 2x power has to be by itself before I rewrite this in log form. So I've got to get rid of that 256 first. So I'm going to divide by 256 to isolate the exponential expression. So 1400 divided by 256. You can write it as a decimal, or you can just leave it as that fraction. It doesn't really matter in the long run at the end. So it is a decimal, so I'm just going to leave it as a fraction. You can try to reduce it if you want to see if it reduces. This one does reduce to 175 over 32. So I'm just going to write the reduced version. You don't have to reduce it. You can leave it as it was. Okay, but I've isolated the exponential. Now to rewrite this in log form, a base E log is a what? Who remembers? If it's a base E, it's a natural log. So that's going to be ln of that fraction, and you can write the reduced version or the original 1400 over 256. It doesn't matter. Equals the 2x. So now I've got to get rid of this 2 over here. So I'm going to divide all of that by 2, both sides. So then what I'm doing, I'm in Desmos, and I am finding the natural log of 175 over 32 divided by 2. And this is my answer. And you can see, so 0.85 approximately. And look, if I had left this as the original without reducing, still the same decimal, approximately 0.85. Okay. So the calculating will be done by Desmos or the calculator for you, but you do have to be able to isolate and rewrite from exponential to log form. Okay. Now, here's the way that you could do this. So that's 0.85 approximately. Now let me show you this. I talked about this in other videos with other types of functions, but it works with logs and exponentials as well. When we say solve, solve means you're looking for the x-intercept, right? The solution, the x-intercept, the 0. All of those mean the same thing. So if I want to know the solution, I could graph this and just find the x-intercept from the graph. Okay, so that's another option. If you don't understand the rewriting, and I've done all of these by rewriting. So if you go through and watch this last video too, and you're like, ooh, I'm not sure I'm going to remember that on the exam. Remember how to plug it in and look at the graph and click on the x-intercept. Okay, so this one was originally 256 e to the 2x. Now, it's not set equal to 0. Here's the thing. If you're going to look for the x-intercept, the equation has to be set equal to 0. So that 1400 would need to move to the left by being subtracted. So minus 1400. And then I'm going to come and I'm going to click and look at that. What does it show for the x-intercept? Same thing I got the other way, isn't it? Approximately 0.85. So you can do it that way. The other option, which I also showed in a previous video with another type of function, I think I showed it with quadratics, is if your equations are not set equal to 0, like this one, you have two sides of your equation, you can write them as two separate functions. So you can write y equals the left side and y equals the right side. And when you do it this way, you're not looking for the x-intercept, you're looking for where these intersect because you're looking for where they're equal to each other, the left and the right. So you may have to zoom out and you're looking for where that intersect. This one you would have to zoom way out because it's up at 1400. So this probably wouldn't be the best way to do it for this particular problem since it's such a large number. But I just want to show that you can do it that way. Okay, so if you click on that and you can see that intersection has the same x value. Okay, so whether we move everything to one side to set it equal to 0 and find the x-intercept, or we set the left side equal to y, the right side equal to y, and look for the intersection, or whether we solved it by changing it from exponential to log and inputting it in the calculator. All three methods got us 0.85. Did you have a question, Maida? It's not in Aware. And you told me you were coming to tutorials. Oh, for the corrections? Okay, give me a sec. Okay. All right. All right, so 3 different options for how to solve that. So then let's try in this next one with one of these graphing methods, since that is technically faster. Okay, so I'm going to type in the left side, which is just 75, and the right side, which is 21 times 1.05. And they use t, you just use x. Doesn't matter what letter is used for your variable. But I did y equals the left, y equals the right, and I'm looking for where they intersect. So here is that point of intersection, and it's the x value of that intersection that you're looking for. Now, have any questions about that? So that I didn't even have to write anything down to do it that method. So that actually may be most of y'all's preferred method. Let me write that down. So 26.091. And I'll just make a note here. I did Desmos. I did y equals the left, did y equals the right, and find the x value of the intersection. We could have done that on all of these in this whole section. So you could go back and try those and make sure you've got the hang of it. Okay, for O, that would be the right side is 1,000. The left side is 10 to the power. Now, some of y'all are struggling getting more than one thing in your exponent. It's your cursor's automatically bumping you out. Just use parentheses, and then everything you type inside there will be up in the exponent. So it's x squared plus 3x minus 7, all in the exponent. And I'm looking for where these intersect. So again, that makes a weird, funky graph. But I know this line, this blue line, is going to be way up at 1,000. So I'm going to have to zoom way out to see it. Okay, there it is up there. And I'm looking for the point where those intersect. Now, because of the shape of that, that intersects in 2 places. So this one has 2 solutions. So at -5 and 2. Thank you. Here. All right, any questions about that method? And you can go back and practice that method. The y equals the left, y equals the right, and find the x value of the intersection or intersections if there's more than one. And those are your solutions. Good? All right, let's flip to the next page. The next page is still logs and exponentials. This is more our word problems, our application problems, where we learned about interest. Now, again, ours is going to be just the same as our test on the unit. The final exam is only going to be setting up the equations. It's not going to actually, you don't even have to actually solve these. It's making sure you get things plugged in the right spot. So hopefully these are pretty straightforward. Okay, so remember the formula here. P is the principal amount or the initial original amount. Okay, R is the rate. Okay, so the interest rate as a decimal. Okay, so like 5% would be 0.05. Okay, N is the number of times that it's compounded per year. So when you hear quarterly, that means 4 times a year. Annually is once a year. Biannually is twice a year. Okay, monthly is 12 times a year. So you have to be able to figure out that N value based on what they say, how often it's compounded. Okay, and then T is the number of years. Okay, so this first equation is compound interest. This one with the E, okay, I call it PERT. It's P times E to the RT. That is continuous. So if you hear it or see the word continuous, you're going to use that second equation. So A says to set up the equation that would be used to find the value of a $1,000 investment at 6% interest after 10 years. Sorry, I got the hiccups. And so the different ones are at different frequencies of compounding. So here, I'm going to do some highlighting for us. Okay, so the initial amount, the principal, is 1,000. Okay, that's going to go in for P. Okay, the rate or the years is 10 years. That's T. And then our rate, our R, is going to be what? If it's 6%, what are we going to write that as? .06. You can put 0.06 or just 0.06. That part doesn't matter if there's the 0 in front of the decimal or not. Oops. Not what I wanted to do. All right, and then last but not least is the N value, how often it's compounded, and that gets plugged in 2 places, in the bottom under R, in the bottom of that fraction, and up here multiplied by T in the exponent. Okay, so that N is the number of times it's compounded, and I don't know why T is not highlighted anymore. There we go. All right, so let's write what our N value is for all of these. Annually, once a year. Quarterly, N is 4. That's 4 times a year. Monthly, there's 12 months in a year. Continuously, we're going to use PERT. We're not going to have N. We're going to use that different equation for continuously. All right, so here, just setting up, we don't even have to solve. This would say 1,000 times 1 plus 0.06. Now, technically, I don't even have to write this one as a fraction because over 1, does dividing by 1 do anything? It doesn't. So I don't even have to put over 1. So I'll just write it like that. Okay, to the NT. Okay, so our T was 10. 1 times 10 is just 10. So that's the equation for annually. For quarterly, now I will have to have the fraction for this one. So my rate will be over 4. And then my exponent will be 4 times 10, which is 40. For monthly, and of my rate over 12, and 12 times 10 is 120. So that would be my exponent. And then for continuously, it's just PERT. So the principal amount is the 1,000 times E to the R T. So you could do it like that, or you could go ahead and multiply the 0.06 times 10, and then it would just be 0.6. That's up to you how, if you want to leave it like this so you can see R and T separately, or if you want to go ahead and combine them. But that would be the setup for those equations. Okay, for number or part B over here, it says set up the equation that would be used to find how long it would take to double your money if you invested 30,000 at 4.76% interest. Okay, so again, we're not having to solve, we're just setting up. So if our principal amount is 30,000 and they want us to double our money, what is the annuitized amount? What are we ending with? What's double 30,000? 60,000. So that's what we want it to equal over here. Okay, and then it's 1 plus, and then my rate is going to be 0.0476, and then quarterly is 4 for N, and then for T. T is the unknown here. We're trying to figure out how long it would take, how many years. And that's it. That's the setup. Now, this could be simplified. It might be simplified. Okay, what we would do to simplify this, because if I was going to try to solve this, I would need to isolate this exponential piece. I would need to get rid of this 30,000. How would I get rid of that 30,000 that's being multiplied? I would divide it over. And guess what? What is 60,000 divided by 30,000? 2, because we are doubling. So technically, this could be simplified to just this. Either one of those is correct. Okay, so if you plug in the principal and what it would be doubled, this is what it would look like. If you went ahead and simplified that, just because you know it's going to be doubled, you can just put a 2 here and you have no principal. You just know you're doubling whatever the principal is. That would work for any principal amount. This is how long it would take to double your money, no matter what your initial investment was. That's how you would solve it. All right, with C, it says suppose 2,000's invested in a 3-year certificate of deposit. It's called a CD. It earns 6% interest compounded continuously. Keywords there, continuously. So we're using PERT. We're going to set up the equation that would be used to find the value of the investment after 3 years. So 3 years, that means T is 3. The principal is the 2,000, so that's my P. 3-year certificate of deposit. So after 3 years, that's telling me the same thing. Time is 3. 6%, so R is 0.06, and it's continuously, so it's PERT. So this would be 2,000 times E to the 0.06 times 3. And that's it. That's the setup. That's all we have to do. We don't have to solve it. It should be pretty easy to solve. You just type it in Desmos. It should tell you the answer, but you don't have to do that. D says you invest 200 at 12.25% earning in continuous interest. That's a huge return. I wish that existed. Set up the equation that could be used to find how many years it would take for your money to increase 5 times its original value. So same concept here. See, we were looking for it to double, and so it ended up being a 2 equals. If we're looking for it to be 5 times, we're going to look for it to be 5 equals. But we'll start out with the numbers they gave us. Okay, so we're investing 200. What is 5 times 200? Yeah, 200, 2 times 5 is 10, so that's $1,000. So they're saying, how long is it going to take for us to get $1,000 from a $200 investment? Oh, hang on, I started to write the wrong one. There's that key word, continuous. So I'm not going to have this 1 plus, I'm going to have E. And then the rate is 0.1225. And T is our unknown. That's what we're looking for. So it could be written like this, or you could go ahead and divide the 200 over, and it would be 5 equals E to the 0.1225 T. Either one of those is correct. I feel okay about setting those up. Again, you don't have to solve them. You just have to be able to set them up. You have to be able to understand what in means and what goes where. All right, flip that over, okay? And we are going to set up the following exponential equations, okay? One says a certain material decays at a rate of 1.9% per year, okay? So growth and decay, it's the same equation as interest, but obviously we're not earning interest. So instead of a 1 plus, we're going to have a 1 minus, okay? So I'll write that up here. So you have your initial amount, whatever it is, we call that A, and then your base rate is always 1 plus or minus your whatever R is, your rate. Okay, if it's increasing, it's plus. If it's decreasing, it's minus. And then it's to the power of X. Okay, so this is exponential growth and decay. So this one is decay, so it's going to be a minus. Our R is going to be 0.019. And the initial amount is 260. So that's your A. And how much would be left in 11 years? So that's going to be X is 11. So this would be 260 times, now 1 minus 0.019 and to the 11th power. So that's the equation we would use. And you could just type that in Desmos and get the actual answer if you needed it. How long it would take to have only 100 grams left. So we want what Y is to be 100. We started with 260. It's at the same decay rate, but this time the unknown is T. So we would plug in 100 for the new amount, and T would be our variable, and we could work that backward to solve for T, but your question is just about setting it up. All right, number 2 says the value of Louise's comic book collection has been increasing by 11% every year. So R is 0.11. Her collection began with a value of 150. So that's your A. Set up the equation that would be used to find out the value of the collection after 5 years. That's your T. So we would say 150 was the start, and it's increasing, so plus 0.11 and then over 5 years. So that would be our exponential growth equation that we would use to solve that. Number 3 says Carmen invests $3,000 in an account that pays 3.6% annual interest compounded monthly. So N is 12. R is 0.036. And this is the initial amount, which is our principal. What equation would be used to find out after the balance after 6 years? Okay, so this is compound interest. So this is the equation from the previous page. So 3,000 is the initial amount. Your rate over the number of times it's compounded time to the power of nt. So 12 times 6 up here in the exponent. And that's what we would plug in to find out what that would be worth after 6 years. 4 says you put $7,500 in a savings account, paying 3% interest compounded continuously, keyword. So we're using PERT. We have our initial amount. We have our R is 0.03. And the balance after 5 years, that's your T. So this time it's 7,500 times E to the 0.03 times 5. All right. All right, moving on here in this next section, they're asking us to graph and identify key attributes. When we talk about key attributes, the things that you should be able to identify as an Algebra 2 student at the end of the year, you should be able to look at any function's graph and tell me X and Y intercepts, domain and range. You should be able to tell me if there is an asymptote, okay? And that's pretty much all that you're going to be asked. Where are the asymptotes, if there are asymptotes? What are the domain and ranges? And what are the intercepts? Okay. There's other things that we have talked about, like if there is a maximum or a minimum, or if the function's increasing or decreasing and things like that. But the main thing that you need to know for this test will be domain, range, intercepts, and asymptotes. Okay. So these first two are square root functions. Okay, so again, I can graph these by hand. I would hope you can graph them by hand, know your transformation rules, okay, but you get Desmos the entire test. So it does not hurt you at all to come to Desmos and plug in that equation. So it is the square root of x plus 4, and then on the outside, plus 2. So we should know that plus 4 on the inside is a shift left 4, and plus 2 on the outside is a shift up 2. Okay. But if you need the help, look at Desmos and come and click here and get these points. So there's the vertex, if you will. It's not technically a vertex because it's an endpoint. It's a minimum point, but there's not a change in direction here. But that's at -4, 2. And then there is an intercept, a y-intercept at 0, 4. Oh, it doesn't even ask for the intercept there. We'll just plot it. Okay, and that's enough for me to graph my curve. A square root function does not have an asymptote, so we don't have to worry about that. We just had to identify where that endpoint was, and now what are the domain and range. So you should be able to look at a graph and tell me how far left to right it goes and how low to high it goes. So this point here at -4, 2, that is the farthest left, and it's included. And then it goes to the right forever. So the domain would be -4 to infinity. And you could use a bracket on the -4 because it's included, and a parenthesis on the infinity because you'll never reach it. The other option is in inequality notation. You could write the domain as x is everything greater than or equal to -4. For the range, same thing. You could do interval notation. The lowest y value there is 2, and it's included. So you could do bracket 2 to infinity because then it goes up forever. Or as an inequality, you could say y is everything greater than or equal to 2. Both of those are correct. Okay, now I'm going to do the same thing with this next one. We have the square root of negative x plus 3. And then nothing on the outside. Okay, so we should know that what this looks like. This one's a little trickier because of that negative inside. So I'm glad you get Desmos. I would definitely use it here because you might get tripped up because of that negative on the inside. Okay, but we can see from the graph on Desmos that we have a vertex at 3, 0, and that's our x-intercept. So I'm going to plot that. And then it looks like there's a y-intercept at 1.7. You don't have to plot that. If they asked for it, you could give it to them. But you can get other points that are not like decimal values. Like there's a point at 2.1. Okay, and you could look for other points at intersections here. So there's a point at negative 6.3. Okay, and then I could sketch my curve through those. And then I could answer the domain and range questions because I can see it comes from the left. It goes left forever. So that's negative infinity. And then the furthest right it goes is 3, including the 3. So you could write that as negative infinity to 3 with a bracket on the 3, or you could write that as x is everything less than or equal to 3. Range goes from 0 up to infinity, including the 0, or you could write y is everything greater than or equal to 0. Both of those are correct ways to write the domain and range. You need to be able to answer domain and range questions in interval or any equality notation. A trick that I think, let me double check in Desmos that this works, but somebody told me about is, let's see if it will highlight. If you have a multiple choice question and one of the things is x is less than or equal to 3, you can type in x is less than 3 and it will highlight it for you. And you can check that that highlighted section is covering your entire graph. Now, I don't think you can type in less than or equal to. Oh yeah, you can. I just, after the less than symbol, I just typed the equal sign and it turned it into less than or equal. And you can see that made it a solid instead of a dashed line because it includes that point. So you could check backward from your answer choices of domain and range. So then we could check, okay, that my domain checks out. Let me double check my range. I said y is greater than or equal to 0. And you can see it's highlighting that section, everything above 0. And does that cover my whole graph? Yes, it does. So that confirms that my range is correct. So that's a little trick to check your domain and range with inequality notation that I just learned about. But Desmos does that. It will like just highlight that domain or range for you, and you can confirm that your graph falls in that domain and range. All right. Now those two were both square root functions. Now we're going to do the same thing and identify key features. This next one, C, is quadratic. And then the next one is exponential. So they have an extra question there of, is it growth or decay? So that means, is it increasing or is it decreasing from left to right? And that one asks about an asymptote because exponential functions have an asymptote, log has an asymptote, and rational have an asymptote. So if it's a log, exponential, or rational, you're going to be asked about the asymptote. Okay, but let's go ahead and do this quadratic one. Remember, your vertex, when you're in standard form like this, or excuse me, vertex form, you can see your HK. And HK is your vertex. So H is -1 and K is -4. So there's my vertex. Now, I also could just go type that in Desmos and see the graph, okay? But that tells me this is shifted left 1, down 4, okay? And that A tells me it's stretched by 2. So I'm going to have a point here. Here. Now, again, if you don't understand how I just got those points, don't worry about it. Go use Desmos and get the points plotted by looking at Desmos. But once you have that graphed, whether by hand or using Desmos, give the domain and range. So the domain here, the lowest, the range would be the lowest it goes is -4, and it's included, and it goes up to infinity. Or that could be written as y is everything greater than or equal to -4. The domain is how far left to right. What is the domain of all quadratics? All real numbers. It goes left and right forever. Okay, or you could use the all real number symbol. All right, I should be able to, you should be able to graph an exponential by hand as well, just like I just graphed this by hand. But again, you don't have to. Take advantage of the fact that you have access to Desmos on the entire test and use that to do your graphs. Okay, so this one is just 1/2 to the power of x. So it's this exponential over here. We can see we have an intercept at 0, 1. Okay, and you can click on some other places to get additional points. Like there's a point there at -1. Oh, I can't get to, there it is, -1, 2. Okay, but I mean, that's enough. You get the idea, and you can zoom out and look. Where does it appear that there's an asymptote? Where does the graph look like it just levels out and doesn't change anymore? Along the x-axis, right? Okay, now if you forget, ooh, is that x equals 0 or y equals 0? Type it in and see. X equals 0 and y equals 0. Ooh, there it is. X equals 0 is a vertical line. That's not it. It's this horizontal one. It's y equals 0. So it looks like y equals 0 is the asymptote. So I'm going to sketch that as a dashed line here and write that as my asymptote. And it is a horizontal asymptote. Now this function is increasing or decreasing? When we read a graph, we read it just like a book, left to right. So if I were to trace this, am I coming down or going up? Down. It's decay. Okay, the domain is still all real numbers. Domain of exponentials is all real numbers. Okay, it goes left and right forever. But the range is inhibited by the asymptote. So that asymptote in this case is at 0. So the range is 0 to infinity. But this time we do not include 0. We use a parenthesis because there's an asymptote. It doesn't actually include 0. Or you could say y is greater than 0. Okay, so here's a couple more exponential on E and F. Okay, so this one was decay, and it was a fractional base. Any guesses looking at these, 1/3 base or a 3 base, on which one might be growth and which one might be decay? Yeah, when you have that fractional base that's between 0 and 1, you have decay. When your base is greater than 1, that's when you have growth. So I know right away, just looking at them, I can answer those questions. Okay, and looking at these equations, is there any transformation left, right, up, or down? There's no translations here. They are not shifted up, down, left, right. There's no negatives. They're not reflected. So I know that the asymptote hasn't moved from the parent function, which is at y = 0. It's going to be that horizontal asymptote is going to be the same for both of these. And you don't have to know all that off the top of your head looking at it. You can always go plug them in Desmos. Okay, so if I were to go and compare these, so a 1/3 versus a 3 base, so change that 1/2 to a 1/3 base, and you see it just barely slightly changed. Okay, the x-intercept, or excuse me, the y-intercept didn't even change. Okay, so the only thing that changed was like how steep that was decaying or decreasing. Okay, and then look and see, what if you make it a base 3? Now it reverses direction. We said it's going to be growth, but notice they intersect at the same, or they cross the y-intercept at the same place. So they both have the y-intercept still here at 1, but this one is growth, and this one is decay. So the domain for both is the same. Domain for all exponentials is all reals. The range for both of these is the same as well because the asymptote didn't move. So it's still 0 to infinity. Or y is greater than 0. Y'all feel okay about those? All right, I'm going to stop this video here, and I'll continue the rest of this in one last video. Okay, I'll post all of these videos to our Canvas, and I highly encourage you, if you are not exempt and you are having to take this test, go watch these videos. I know it might be time consuming because this is a long review, but I go over how to do all of them in Desmos.